Good evening, ladies and gentlemen. While I say good evening for our people here and good afternoon for Professor Blundy. I am Farooq from Geological Survey of India and a member of SGAT. On behalf of Society of Geoscientists and Allied Technologists, I have the privilege of welcoming you all to the virtual 9th episode of the Distinguished Lecture Series, a prestigious academic program from the Society of Geoscientists and Allied Technologists. Now, I would like to give you a brief sketch of this society. The Society of Geoscientists and Allied Technologists is a not-for-profit professional body dedicated to the cause of geoscientific studies and sustainable mineral development activities in India. Started in 1980 by a handful of eminent geoscientists, it has grown in size and activity by attracting scientists from a range of disciplines such as geology, geophysics, mining engineering, mineral processing, metallurgical engineering, environmental science, and so on. One of the flagship activities of SGAT, over the past 3 decades is directed towards instilling an awareness about geology, mineral development, environmental aspects, including climate change among the student community at the school as well as university levels. Odisha is home to a host of minerals and has earned the epithet of steel and aluminum capitals of the country. Visualizing the mineral industry scenario, with the help of its knowledge bank, SGAT published a comprehensive compendium on geology and mineral resources of Odisha in 1995. The book saw its 4th revised and updated edition in 2021. It plays a significant role in assisting the government of Odisha while formulating the state's mineral investigation and exploration programs. The society brings out a biannual technical bulletin for the last 23 years. And finally, the society has introduced a distinguished lecture series by eminent professionals from India and overseas in the fields of geosciences and related areas. 8 such lectures have been delivered so far. Today, we are waiting to listen to the 9th distinguished lecture by Professor Jonathan David Blundy. Now, I would request our president to have a few words with us. Dr. O.N. Mahanti, President, SGAT, please.
Thank you, Dr. Farooq, for those interesting words about the SGAT. I join Dr. Farooq in welcoming all our listeners who are participating on this online program. As a matter of fact, what COVID has gifted to us, it is a blessing in disguise, because before wouldn't have even imagined to have professors from Oxford or from elsewhere talking to us. And so that's why, as they say, the new norm has started and one such is here. And we are delighted that we have been able to hold 8 such distinguished lectures. And I'm further delighted that one of the earlier speakers, Dr. Dimri himself, is present also here. And the 9th lecture in this series is being delivered today by a world-renowned geoscientist, Professor Jonathan Blundy. And the topic of volcanoes to green mines, actually, it's a very interesting thing that it coincides with the day number 3 of Make in Odisha conclave. And as Dr. Farooq has rightly said, Odisha is home to a number of rich minerals. And the last 3 days of deliberations in Bhubaneswar brought to this place the who's who, so to say, of the industry of India. And I don't know exactly the percentage, but a very large chunk of that, they belong to the mineral-based industries, whether it is steel or aluminum or copper and so on and so forth. And all the industry chieftains are here. So it actually essentially coincides with the fact that Professor Blundy is going to talk about from volcanoes to green mines. Those of us who are conversant and are also sensitive to the fact that the United Nations have set up the SDGs as the goals of the Sustainable Development Goals for the entire world. And I'm very happy that we have a lecture which actually essentially coincides with that, or is in line with such thoughts. So I don't have to add anything right now, because we have really an authority, world authority, about to speak to us on the topic of volcanoes to green mines. Thank you, Dr. Farooq.
Thank you, President. Now, I'm excited to be here this evening to have the opportunity to introduce our guest speaker, Professor Jonathan David Blundy from the University of Oxford, United Kingdom. Professor Blundy, after having completed his education in the University of Oxford with geology, obtained his degree of PhD on the geology of the Southern Adamello Massif, Italy, from the University of Cambridge. He was awarded a scholarship, Kennedy Memorial Scholarship, from the Massachusetts University Institute of Technology, USA. Then he had the Royal Society University Research Fellowship in '94. As guest professor, Nagoya University in Japan, 2007, is a fellow of the Royal Society. That is the most important award he has earned. Royal Society Wolfson Research Merit Award, Royal Society Research Professor, University of Oxford in 2020, visiting professorship of University of Tokyo in Japan. Among the professional activities, he is a member of the Ocean Drilling Programs of Steering Committee in 2003. And he has a series of editorial assignments, which include in the editorial board of Geology, which is published by the Geological Society of America, associate editor of Island Arc, editorial board, Journal of the Geological Society, subject editor, Earth Sciences, Royal Society, Open Science, and principal editor for petrology in the publication Elements. He was also with the advisory board, Research School of Earth Science, Australian National University. Among the research programs, research activities which he has carried out, I have only, keeping the time in view, I have only selected 7 to mention here. There are so many. The researches which he has carried out are the effects of heat transfer on the forceful emplacement of granitoid pollutants, an experimental study of mineral fluid partitioning during subduction, igneous pathology, a new look at magmatic processes beneath silicic volcanoes. How does the Earth's crust grow at divergent plate boundaries? A unique opportunity in FR Ethiopia. This is a very fascinating research. Magma dynamics at persistently degassing basaltic volcanoes, a novel approach to linking volcanic gases and magmatic volatiles within a physical model. His 6th is in situ mining of magmatic brines with the BHP Billiton. And finally, because I have chosen only a few, from volcanism to green mining, rethinking igneous geochemical cycles. His talents and expertise in the subjects are demonstrated by 27 PhD degrees, 27 PhD degrees supervised by him. He has also supervised or co-supervised postdoctoral researchers, about 38. And he has a publication of 218 plus 9 publications in press, 9 to be published. The area of research of Professor Blundy include igneous petrology, economic geology, volcanology, experimental petrology. Now, without further ado, please join me in welcoming Professor John Blundy. So here we are going to listen to Professor Blundy, backed by 33 years of research experience. He is a strong proponent of green mining. I request Professor Blundy to take over. Professor Blundy, please.
Great. Professor Blundy, is your microphone on?
Okay, I've been unmuted. Can you hear me now?
Yeah, absolutely.
Okay. All right. Well, I hope you can see the screen okay, and
Yes.
I hope you'll find this an interesting talk. I'd like to start just by saying it's a privilege to have been invited to give this distinguished lecture. I've never myself visited India, so this is as close as I've ever come. But thank you very much for having this opportunity to address you. I'm very impressed at how many people have taken a little bit of their Saturday evening to listen to what I hope will be an interesting story about how volcanoes can help us to achieve net zero, a challenge that is almost existential in its extent, and something that as a global community we need to be working towards in the next as little as 25 to 30 years. So after that very kind introduction, I just thought I would show a picture of myself at one of the many volcanoes where I've worked. This is actually in the Western Pacific archipelago of Vanuatu. This is a volcano called Yasur, and Yasur has been erupting almost continuously since at least the 18th century. Most of my research over the last 30 years has been around how volcanoes work and what the plumbing system of the magma underneath the volcano looks like. But about 10 years ago, I started to take an interest in the relationship between volcanoes and resources. And these resources are both metals you're very familiar with, of course, and also geothermal energy, a source of green energy that produces very little carbon dioxide and also provides a base load that doesn't rely on the sun shining or the wind blowing, and doesn't need fossil fuels and doesn't need nuclear fuels. Okay, so that's the kind of the background really. I'll just talk you through some of the challenges and how I think that volcanoes can help us. So net zero is, in its simplest terms, a strategy to achieve net zero carbon dioxide emissions to the atmosphere. Obviously, carbon dioxide is responsible for global warming, and reducing and ultimately eliminating CO2 emissions is one very important step towards reducing global warming and ensuring that the planet can be enjoyed by everybody for many, many years to come. I just thought I'd start with this statement of the problem. It comes from a UK government bulletin. We could read this in many different guises from organizations like the World Bank or the United Nations. And here's the statement of the facts. The science could not be clearer. By the middle of this century, that means 2050, the world has to reduce emissions to as close to zero as possible, with a small amount of remaining emissions absorbed through natural carbon sinks like forests and new technologies like carbon capture. If we can achieve this goal, global emissions of greenhouse gases will be net zero. Delivering this requires urgent global action, including ending coal-fired power generation, retiring petrol and diesel engines from all cars, and halting deforestation. That is a very, very ambitious goal for us to achieve as a global community. And the part of the challenge I'm going to address today is outlined at the bottom. We will need all sorts of metals, we'll call them critical metals, and we will need low carbon forms of energy to achieve this transition. And as an earth scientist, I'm going to outline what we can do to help this transition. And my main point really is that earth sciences, the study of the earth and rocks, is actually critical to achieving the net zero transition. And I hope that in the next few years, many young people will feel inspired to take up the study of geology in recognition of how important it will be in achieving the net zero transition and improving the habitability of our planet. So let's just start with what a strategy might look like. And I've picked a strategy from the Netherlands. That's what NL stands for at the top there. And I've chosen the Netherlands not because it's a special case, this is a fairly typical case, but because their government has provided a very nice infographic that describes the problem we face. So on the right-hand column here, perhaps I'll see if I can make a little pointer. Here we are. On the right-hand column, here is the technology that we're going to need. Some familiar technology, electric vehicles, solar panels, wind turbines. In the Netherlands, they intend to perform electrolysis of water to generate hydrogen, and also energy storage in batteries and energy transmission in cables and infrastructure will be required. This is a green mix. So far, so good. In the middle column here are all the different metals we need to achieve this technology. And the metal is connected to the technology by a line, and the fatter the line, the more you need. And there are some very familiar metals here like copper and nickel. There are also rare earth metals like neodymium and praseodymium that are used in batteries. And there are perhaps less familiar, indeed precious metals like platinum and iridium that are used to make the electrodes for water electrolysis. So far, so good. In the left-hand column are all the countries that supply the metals that drive the technology. And the first thing I want you to notice is that the word Netherlands does not appear in this column. So the strategy for net zero of this country involves resources which it simply doesn't have. And that creates some real geopolitical challenges. For the Netherlands to achieve this strategy, it has to maintain a good political working relationship with all of these countries. The fatter the arrow here, the fatter the line, the closer the relationship needs to be to supply the materials to drive the technology. And this is a very, very important point. In India, I suspect there is also a net zero strategy, but unlike the Netherlands and indeed the United Kingdom, you are blessed with many, many resources. And the middle column here for India would include metals that you provide in abundance. So this would be one of many strategies. It involves familiar and new metals that we will call critical metals. And let me emphasize that we cannot simply recycle what we have. For many of these metals, there is not enough metal in circulation. Recycling at the very best would be about 50% for some metals and much less than that for others. And this infographic describes the real supply risk, the security of supply challenge that we face. So that's a statement of the problem. The problem ultimately has been diagnosed over many years by the IPCC, the Intergovernmental Panel on Climate Change. And the IPCC has told us that the patient is unwell, the patient is very unhealthy, the patient is sick. In fact, the patient is perhaps terminally sick. We understand the diagnosis. Now it's time for some medicine. It's time to stop thinking about how unwell the patient is, how unwell the planet is, and what can we do? What medicine can we prescribe? And like most medicines, it's not necessarily tasty, but there are some possibilities. And I want to talk about the possibility of using volcanoes. Volcanoes, put very simply, are produced by magma, and magma is the undisputed king of mass, that is material, and heat transfer in the solid earth. Nothing moves material and heat around the solid earth better than magma. This is a volcano. I've chosen it just because it's one that I know. This is off the coast of New Zealand. This is White Island. And White Island last erupted about 3 years ago. And in addition to producing lava and ash and tephra, when it's not actually in eruption, White Island discharges plumes of smoke to the atmosphere. This is steam and particles and little suspensions of liquids, droplets. And in those fumes, in those clouds, each year, there are 100 tons of copper and 4.5 kilograms of gold. And those steam plumes, those volcanic gas discharges are very hot. So here we have metals that are contained in solution, and that solution is very hot. Rather interestingly, we don't mine volcanoes. Instead, what we do is we allow time to turn off the volcano, to erode the volcanic edifice, and to expose the interior of the volcanic system a few kilometers down. We wait until all the heat has gone. We wait until all the metals have come out of solution and precipitated. And then we dig an enormous hole in the ground. We extract the rock and crush it. We throw away 99% of the rock. We build huge tailings dams on the surface, and we leave an environmental scar for many, many years to come. And not least, we don't use any of that heat because it's all gone. So we have to use electricity generated usually by fossil fuels. I'd like to emphasize that is an extraordinarily inefficient way of harvesting Earth's resources. And if I was to be visiting this planet from another planet, and I looked at the opportunity provided by volcanoes and the reality of mining, I would think that was a very strange way to harvest Earth's bounty. So let's start with the metallic bounty. I showed you metals coming out of White Island volcano. And White Island's one of many, many volcanoes worldwide that is discharging gas with metals without actually erupting. Excuse me. Let's start with perhaps the big daddy of them all. This is Mount Etna on the island of Sicily in Italy. And what this plot shows on the left-hand axis is the kilograms per day averaged over a long time of metals that have been discharged by Mount Etna. And we see many different metals here. I'll just point to one. Here's copper, a very important metal for storing, transmitting, and generating electricity. And this red dot is the emission of copper, time averaged. That's 20,000 kilograms, 20 tons of copper every day over the lifetime of the volcano are just simply discharged to the atmosphere. They are actually thrown away. We can't recover them very easily. We can't put an umbrella over Etna and harvest those. Fortunately for us, a lot more metal than comes out at the surface is actually stored underground, trapped underground in hot fluids. And that's the subject of this talk. The right-hand plot here is really rather remarkable. On the horizontal axis is the mined production, that is dug out of the ground in kilograms per day of all sorts of metals. And on the vertical axis is the amount of metal discharged to the atmosphere. And what you notice is that each year more metal is discharged by volcanoes to the atmosphere than is actually mined for all of these metals, with the exception of iron, because iron is one of the few metals that doesn't ultimately come from volcanoes. Aluminium, that was mentioned in the introduction, is another. So these metals are being discharged to the atmosphere. We can't recover them very easily, but as I said, much more metal than comes out in the volcanic plume is actually trapped underground. So volcanic gases carry a diverse portfolio of metals and what we'll call metalloids, but much more metal is retained in trapped condensed fluids. So these are denser, as it turns out, very salty fluids underground. About 2,000 volcanoes around the world are degassing in this way. And that gives you an idea of the potential to harvest this sort of resource. Can we access it economically? And the short answer, the spoiler really, is yes. And can we combine metal extraction with geothermal power production? And again, the answer is yes, but a slightly more cautious yes, as we shall see. So the other resource that volcanoes provide is energy. And in many parts of the world, geothermal energy, energy associated with volcanoes, is harvested and used for electricity production. And this rather splendid image on the right here is Iceland, one of the leading producers of geothermal energy in the world. And this is the Nesjavellir power plant on Iceland, one of many. In fact, many countries around the world generate geothermal electricity using volcanic heat. And this is an area that is set to grow in the next few years. And in a final slide, I will actually show you the potential for geothermal energy in India. I was asked to give some data relevant to your country, and I'll do that right at the end. So how does this actually work? Well, for geothermal energy, we would have a source of heat, which is hot magma, and that's shown at the bottom here. And as the heat leaves the magma, it transfers the heat to water in the groundwater, in the rocks above, and this water convects, and that's the source of the fluids that ultimately come into the turbines here. Now, in most geothermal plants, what I'll call conventional plants, this water comes from the surface. It could be seawater in the case of Iceland. It could be meteoric water in the case of many other places. And that water is rainwater or seawater that accumulates at the surface, sinks down, becomes heated and rises back up. And we have a convection cell. And a conventional well, the black line here, would go into this reservoir here, take out fluid, extract the heat, as they're doing here, and then normally re-inject the fluid to keep the reservoir recharged. Most of this fluid is not especially rich in metal because it started as meteoric or seawater. In the region just above the magma, though, there are fluids that derived from the magma itself. And these are the fluids that ultimately give rise to the gas plumes we saw in the previous slide. This fluid is much hotter, as you might imagine, and because it's hotter, it contains more dissolved fluids. And we call this supercritical fluid, and the next generation of geothermal power generation will drill not just to depths of 1.5 or 2 kilometers, but to depths of 2 to 5 kilometers, and actually directly access very, very hot supercritical fluid. And that gives us the potential to take not only the heat, but also the metals from that fluid. Supercritical geothermal systems, that's not just a pipe dream. There are exploration projects in Japan, Italy, USA, Iceland, New Zealand, and Mexico today. And it's expected that the first supercritical geothermal power will come online in the next few years. The beauty of supercritical systems, the fluid is so much hotter that we get up to 10 times more joules of energy per kilogram of fluid. The beauty of supercritical geothermal is obviously it's green, it has very high enthalpy, it's plentiful, there are many places around the world, and it's baseload. We don't need the wind to blow or the sun to shine. It's continually producing. There are challenges. It's expensive to build a power plant like this. Some of the opportunities to bring the cost down are just emerging, particularly around drilling technology. Fluids don't flow as readily down here. The rocks are not as brittle. There aren't as many fractures. And sometimes the re-injection of fluids can trigger seismicity, induce seismicity, and that represents a significant issue in some areas and has actually closed down geothermal power production in some countries. So let's have a look at how this works in terms of the magmatic system. So let's go back to our volcano here, doing its volcano thing, producing gas, occasionally erupting. That is the very end product of a whole transcrustal system in which magmas are injected at the base from Earth's mantle, and they are crystallizing. And as they crystallize, the melts start to migrate upwards. They're less dense than the crystals, so melts are moving up, That's these green arrows. And eventually the magmas become saturated with gas, and then the gas forms bubbles, and the bubbles start to migrate upwards, and that's the blue arrows. And if the gas just migrates out the volcano, we get a gas plume. An interesting feature of volcanic gases, though, is they aren't just pure water or pure CO2. They have dissolved in them salts, of which the most important for our purposes is NaCl. And in a phase diagram that shows the behavior of pure water mixed with pure NaCl, mixtures somewhere in this range, a fluid, perhaps with this composition, as it ascends, as the pressure goes down, depending on its temperature, it encounters this black line, and no longer is it thermodynamically favorable to be a single fluid. It actually separates into a vapor with very little salt, that's V, and a liquid, which is very rich in salt. So about 50% NaCl, so more than 10 times saltier than seawater. This phase separation is very important. It takes place at a depth of about 3 kilometers, and all of the metals that are in this original fluid, the little blue arrows here, because the metals all like chlorine, they all partition into the liquid. So the liquid becomes very rich in metal, and the vapor poor in metal. And that's why the vapor that comes out of volcanoes like this it contains quite a lot of metal, but much more metal is trapped underground in the liquid. And I'll refer to those liquids as dense metal-rich brines. And they get trapped at about 3 kilometers depth because of their density, and they start to accumulate in porous rock at those depths. And just to capture that idea of condensation or the way in which the brines form, think of water vapor condensing on a cold window. This might happen in your house, and here are the little droplets that are taking water vapor out of the air and leaving behind slightly drier air. And so in this volcanic sense, these little droplets here would be the equivalent of this dense brine. This is a process driven by temperature, but in the earth, it's driven primarily by a change of pressure. So let's see what that actually does beneath a volcano. So here's my volcano again, and I've created some hydrodynamic simulations where in fact we have a source of magmatic heat down here. It's discharging fluid, and that fluid ascends up a cylindrical conduit, a high permeability channel. And as it moves up here, it expands and it cools slightly, and it separates into the brine and the vapor. And the vapor just comes out the top, but the brine, as I said, starts to accumulate within porous rock. And these are little time slices of the process, and the brighter the color, the saltier the fluid. And what we see with time, these are axisymmetric models, so they're symmetrical about this axis, just like we've seen here. This is the region of brine accumulation. It's a lens of brine. It's a bit like a donut at a depth of about 2 to 3 kilometers. And we run these simulations for various different volcano parameters, temperatures of fluid, permeability, porosity, and so on. But we always get a brine lens, and it can be very, very long-lived. Here, it's still going 250,000 years after degassing began. And even when you turn the volcano off, these brine lenses persist for a long time. In fact, the only thing that destroys them is groundwater getting into the system and eroding, diluting the flanks. What is quite remarkable is that these brine lenses exist under every single volcano in the world. And we know that from geophysical surveys. The most useful geophysical surveying tool is to look at electrical conductivity. We use the Earth's electromagnetic discharges to drive electrical currents in the Earth, and we measure the currents at different places on the Earth's surface, and then we could work out the electrical conductivity or resistivity structure of the subsurface. So here are two places where I have projects. This is in Bolivia, and this letter here, U, is a volcano. It's actually a volcano that has not erupted for 250,000 years. We see three bright red regions, bright red meaning low resistivity or high conductivity. The deepest conductor at 15 kilometers, labeled C2, this is actually magma. It's partially molten rock. The very shallowest conductor, labeled C1, is actually smectite clay. Clays are conductive, and these clays form because fluids react with rock and produce clays. What's really of interest for this talk, though, is this conductor here labeled C3. This is a lens of hot, highly salty brine formed by the process I showed in the last slide. This is Uturunku. This is a volcano in Japan. This is Kusatsu Shirane on the island of Honshu. Again, slightly different scale, but the brighter colors are highly conductive or low resistivity regions. The magma itself is somewhere down here. Here's the brine lens, called C2 in this case, the same as that. And here's the clay cap. This is where the very salty metal-rich fluids are stored. We have surveys of over 40 volcanoes worldwide. They all have a brine lens. So the question is, could we somehow drill into this brine lens? Could we take out the fluid? Could we recover the heat? And could we recover the metals? If we can do that, we don't need to mine. We don't dig holes, big open pits. We have no waste tailings at the surface. And we also have a supply of energy to run the mining operation. We don't need to rely on external sources of electricity. And we can use many different techniques to image these systems. The question is, what do they contain? And is it a prize worth going for? So in this, I'm helped by a rather splendid natural laboratory. This is a geothermal power plant in Japan, in Honshu, called Kakonda. It's remarkable because in 1995, Kakonda was drilled. Kakonda was drilled to a depth of almost 4 kilometers in 1995. And they reached a temperature at the well bottom of 510 degrees. This is a system where a very, very young granite magma is providing the heat. And it's a system where, again, we see a very conductive region of brine. Here's the clay again, here's the brine. This well didn't go right into the brine lens, it's just on the edge, but we can learn an awful lot about what is in this system from rocks recovered from this well. Not only that, but at the bottom of the well, when they drilled it, brine oozed into the well, and they were able to sample that brine and see what its chemical composition was. Kakonda is a 50 megawatt geothermal power plant. Currently, these turbines are fueled by wells that go to about 1.5 or 2 kilometers depth just here. They don't yet harvest power from the bottom of these very deep wells, but that is a plan to be rolled out in Japan in 2024. And Japan aims to have its first supercritical geothermal site, probably at Kakonda, operating shortly after 2024 with a power of 100 megawatts. This is Japan's response to net zero. This is a form of green energy. It's made all the more urgent since the demise of the Japanese nuclear industry following the Fukushima Daiichi nuclear incident in 2010. There's one problem here, and you'll see how we're going to address this problem. To generate a supercritical power plant in Kakonda is expensive, and the energy it will produce is 2 to 4 times more yen or dollars or whatever per kilowatt hour than oil and gas. That means that even though they can generate green energy, it is more expensive than oil and gas. So in Japan, a priority is to make this cheaper, and we have a wonderful opportunity to achieve just that. So let's start by seeing what's in the reservoir underneath Kakonda. Well, the first thing we need to do is to explain how do we achieve these low resistivities in regions like C1. Well, the remarkable thing about brines, the reason they show up in electrical conductivity surveys, is, as you can imagine, they are very electrically conductive. Ions of Na and Cl are able to move readily, and you don't need an awful lot of fluid to achieve high electrical conductivities. And that's what I show in this plot. This is the electrical conductivity. It's the reciprocal of resistivity measured in Siemens per meter. And this is the porosity of the rock. And what you see, let's just follow the red curve. As you add relatively small amounts of fluid, the conductivity rises dramatically. So if we know the conductivity and we know how salty the fluid is, in this case, just a 4% NaCl fluid, we can work out how much fluid is down there. In Kakonda, the fluid is actually saltier even than 20%. So if we follow the gray dashed line to achieve this level of conductivity, we probably need 2, 3, 4% porosity. So that tells us how much brine is stored there. And in fact, when we take rocks from the well was cored, we can actually measure porosities of around this level, around about 4%. So that's how much fluid is down there. Now, let's see how hot it is and what does it contain. Well, to find out what it contains, in addition to taking direct samples, we can actually look at rock recovered from the core, different depths here. And within those rocks, particularly in the quartz, we find tiny little droplets of fluid. We call these fluid inclusions. And I just shown some pictures of fluid inclusions. So this is about 20 microns. That's a human hair's width across. And it's fluid with salts and a little bubble of gas. And that's because as it cools, it actually separates into the salts and the gas. But we can actually analyze the contents of these fluid inclusions, and we can use that information to get the temperature that the fluid was trapped at and its salt content. So we can determine by studying the fluid inclusions the temperature and the saltiness. We can also identify the daughter minerals. So some of the minerals here are NaCl or KCl, but these little black minerals here, this mineral here is a copper sulfide, the little triangular one you can see. And what we can also do is use a laser to actually analyze the entire contents of the inclusion, including its metals. So let's start with the temperatures of these fluids. Well, remarkably, when the little fluid inclusions we analyze give exactly the same temperature as the well itself. So the ones at the bottom are giving temperatures around 500. And as we move up, we can see the temperature drop, just like the temperature drops as you go up the well. We could also see how salty the fluids are, and we see they're broadly 50% NaCl. The salinity decreases ever so slightly at the top. So this reservoir here contains very salty, hot fluids. That tells us that these fluids are, if you like, live reservoir fluids. I don't know whether this is on. There we go, you can see that. How about their chemistry? Well, this is a very busy plot, but it's actually rather remarkable. So on the vertical axis is the concentration of metals in the fluid in parts per million. So this is in the brine. And that is 100,000 parts per million. This is, yes. Oh, sorry. I thought someone was calling my name. This is 1 weight percent here. And this would be 10 parts per million down here. Sorry, 1 part per million down here, 10 parts per million. And these are all the different metals we've measured. And what we see, we'll just focus on Kakonda for the moment, the blue squares. So let's look at copper. So the copper content is just less than 1 weight percent. It generally varies with temperature. The zinc content goes up to just more than 1 weight percent. Manganese, a very important metal for steel production, it's about 3 weight percent. In terms of more exotic metals, we have just more than 1 part per million gold, and we have about 400 parts per million lithium. We also have silver, lead, and all the other metals you can see. Caconda is not the only place that we've looked at. We've also looked at geothermal sites in Italy, in Larderello, the green symbols, a volcano in the Caribbean, Montserrat, the red symbols, and a volcanic island in the South Atlantic Ocean called Ascension. They all show a broadly similar pattern of metals. Some are richer in others, some are poorer than others. All the volcanoes have an incredible diversity of metals at concentrations that are economically viable. The final symbol on here is a black hexagon. This is the Salton Sea in Southern California, which is already mined for geothermal energy and metals, but the Salton Sea site is not a volcano. And not surprisingly, the concentration of fluids, the concentration of metals in the fluids is much lower. There's heat here from volcanic heat, but there are no volcanoes at the surface. And there is the plant in the Salton Sea. It's a geothermal plant, but they also recover lithium from this site. And a lot of this lithium, it goes into the car batteries in Tesla electric vehicles. Okay, how much fluid and how much metal is down there? Well, we can make some very simple estimates of the resource. Let's imagine now that we have a conductor that we've determined by geophysics, and we assign some reservoir volume. I've just drawn a circle here for simplicity. Let's say we use the geophysics to work out the porosity, how much fluid. We use the fluid inclusions to determine the salinity and indeed the temperature. We use the fluid inclusions to determine how much metal is there, and then we know the metal price. We make some assumptions. Here are some assumptions I've made at the bottom. How much, how big, how valuable is this resource? Well, this isn't a typographical error. This is the value of the resource in billions of US dollars. So here's Caconda. This resource here contains something in excess of 50 billion US dollars. The assumption I've made is that all the fluid can be extracted, and that is almost certainly not possible. I've also made the assumption that there is no metal processing cost, and that is also not correct. There is some cost in recovering the metals. Nonetheless, even if the recovery is a low percentage and the metal processing cost is quite high, I think you'll appreciate that a few percent of 50 billion is still a significant resource. Here's the case of the Salton Sea, where this is already being done, and you can see the Salton Sea is much less valuable than Caconda, than Larderello, than Montserrat, or than Ascension. This is an enormous untapped resource provided by volcanoes that currently is not exploited anywhere in the world, but it should be. So going back to that challenge at Caconda, how can you get the cost of energy production down? Let's have a look at what comes out the well. So here are metals again. This is the price of the refined metal in dollars per kilogram. The target production of the geothermal wells is 200 tons per hour. So if we know we're getting 200 tons per hour, we know what's in the fluid, we know the value of the metal, we can work out how many dollars per hour are being delivered to the surface by all the different metals. And the reference is the value of the electricity that comes out, or the price, the target price for the electricity, shown as the gray line. And what we see is that several metals provide more value than the electricity. And this is a logarithmic scale. Gold, rubidium, silver, and manganese have many, many more times greater value than the electricity. The project I'm working on with Japanese scientists is designed to recover just some of these metals, to take the price of geothermal electricity down, not just to oil and gas, but well below. This is an opportunity to make geothermal power significantly cheaper than oil and gas. Why isn't this done more widely? Well, here's a rather interesting fact. Most of the metals that are dissolved in geothermal fluids precipitate in the well on the way up, and they produce something called scale. And this is a section through a geothermal well. This is actually from Greece. It doesn't really matter. This is steel, but the lining of the well is actually precipitated directly from the fluids. This scale is a real problem for geothermal power because it reduces the diameter of the pipe and the flow of fluid. If you're a geothermal engineer, you want rid of this, and most geothermal power plants tip acid down the well every few months to reduce the scale. Now put another hat on and imagine you're a mining geologist. This is the ultimate high-grade ore. Here are some analyses of the composition of the scale shown in gray. This scale contains 13% copper, 20% zinc, 20 parts per million gold, and a whole load of other metals. And I've actually shown on this plot the fluid analyses in colored symbols, the fluid that flowed into the well in turquoise, and the fluids we measure in inclusions. So they're all giving the same story. So isn't it remarkable? This is high-grade ore that an economic geologist, a mining company would love to have. This is a geothermal scale that power companies want to go away. The huge engineering, and in fact, it's a metallurgical challenge, is to make sure that we recover the metals from these fluids rather than have them scale the wellbore. That is a tractable scientific problem, and that's something we're working on right now. So finally, I'll just make reference to India. You might have listened to this talk and said, well, this doesn't work for India. We don't have any volcanoes. Well, of course you do. You have a fine volcano down here in Barren Island in the Andaman Islands. But not only that, you have regions of India which are very rich in geothermal potential, with thermal springs that, in the case of Pugar up here in Ladakh, will soon become India's first geothermal power station. Now, the fact that these aren't volcanoes means that the fluids are not as rich in metals as I described, but that doesn't mean there's no metal. In fact, a very interesting issue arises, and I'll just show that in this diagram here. This horizontal axis is how much fluid you've got, how much fluid is flowing into the well or the plant, whatever the site of interest is. And the vertical axis is the concentration, how much metal is in that fluid. So volcanoes, as I've just shown, have a lot of metal, so they're high on this axis, but the fluid flow rate is not that high. Conventional geothermal would have less metal, because it's less hot, but more fluid flowing through because of the convection. Hot springs, such as these we see in India here, would have even lower concentration, but the fluid flow is really very high. We can even look at sedimentary basins where the fluid is just flowing through sedimentary rock. Now the concentration is lower, but we have a lot of fluid. And to continue this to an extreme, imagine seawater down here, hardly anything dissolved, but we have a lot of it. The challenge, the industrial and the economic challenge, is to work out where to place yourself on this black arrow. A lot of value, but rather little fluid, or down here, a lot of fluid, but rather little metal. It may well be that we don't need to mine volcanoes. We may be able to harvest metals from the Indian thermal springs in this region. And in fact, this plot may in fact be in the middle of this plot rather than in volcanoes, even though that is my main target currently. Okay, this is my final slide, just to summarize. Subvolcanic brine lenses are ubiquitous. All volcanoes have these lenses of brine. And the brines contain economic metal concentrations, and those metals are polymetallic, base metals, precious metals, critical metals, etc. They're all in the brines because nearly all metals love chlorine or chloride ligand. And in fact, what I like to say is that brine is the universal elixir. Brine is the most important agent of metal transport on Earth. In volcanic settings or thermal spring settings, the brine is co-located with geothermal resources, sources of energy. We need to put a significant investment of time and energy into developing strategies for metals extraction to the surface. Inhibiting scale is the technical term. And I've shown you just two possibilities here. If we're in Japan, we can recover metals to offset the geothermal energy costs. In other parts of the world, we can simply create mines that are simply wells, and take off the fluid, harvest the geothermal power, and to run the operation. And these are reasonably can be considered as green mines. And on that note, I will just thank you for your attention, and I'm very happy to take any questions.
Thank you, Professor Blundy, for an excellent, very interesting talk. I think we have got some questions. I would like Dr. Bibhu Ranjan Naik to take over and conduct the questions, please. Dr. Bibhu Ranjan Naik, please take over.
Yeah, thank you, Dr. Farooq. And yes, we have a few questions. One Ayaskan Das, he has written, how to be a volcanologist? What will happen if all the world fossil fuels reserves get exhausted? Might be a student, so yeah.
Well, those are
very general questions.
Two good questions. Let me start with the first question. How to be a volcanologist? It all really starts with studying sciences at school. Maths, physics, chemistry are very important study subjects, but then going on to university to study geology or earth sciences. Volcanology is a part of the earth sciences, and you build up to that speciality, that specialism, by having a good grounding in the physical sciences. What will happen if all of the world's fossil fuel reserves get exhausted? That day will come. It's going to become quicker if we stop using fossil fuels and make this energy transition to green sources of energy. I suspect even after 2050, we will still need fossil fuels, but we will actually capture the CO2 they produce and store it underground rather than just discharging it to the atmosphere.
I think, Dr. Naik, my request would be you go through the questions and you have to select, I think, a few.
Yes, yes.
Filter, because there are some very, very general.
Obvious questions, yeah. So is there any other means to locate geothermal energy sources other than the visible hot springs?
Another very good question. So the best techniques for investigating geothermal resources are looking at the electrical conductivity, but that's a very expensive and time-consuming geophysical process. Hot springs are the most obvious surface manifestation of geothermal resources. High heat flow at the surface is also a good indication of geothermal resources. So that map of India that I showed earlier is probably based on heat flow measurements across the subcontinent.
So there is another question from Ramnath. He says that whether the drills were actually done up to 3.8 kilometer depth to validate the simulation.
Yes, so in Kakonda, the well was drilled to, as your question says, to 3.8 kilometers depth. That was really an exploratory hole, and the objective was exactly as your question says, to validate the simulation, to try and see what fluids are there. We're currently planning a number of projects at other volcanoes around the world where we aim to drill holes and then use the information from those wells to refine our reservoir simulations. And so what we do is we make measurements in the well, and then we modify our reservoir simulator, our hydrodynamic simulations, so that we can reproduce the observables in the well: fluid flow, temperature, fluid salinity, etc.
So one Mr. Pearshaw has asked that brine lens is more dominant in felsic or basic volcanism?
Another very good question. Silicic volcanism, for the most part, and I'm qualifying that slightly in that you have brine lenses in Iceland, where the volcanism is mostly basaltic, but the biggest brine lenses we've seen have been beneath silicic or andesitic volcanoes.
Next is from Dr. Sudesh. Is it feasible to explore the dormant volcanoes for targeting rare or critical metals? Any examples of good practice in globe?
So let me just see, is it practical? I know. Oh, actually, yes. Is it feasible to explore the dormant volcanoes? The answer is yes. The answer is, I think this is something we should be investing significant time into doing. We don't need to drill into live volcanoes. The volcano I showed you in Bolivia has not erupted for 250,000 years, but it has a huge brine lens. That's partly because it's in a desert and there's very little groundwater recharge to erode the brine lens. I would like to start an exploration strategy in many long dormant volcanoes around the world to do exactly what Dr. Wadawan is suggesting.
Yeah, there is a question from the president that in Odisha, this state here where we are,
yeah.
That you have shown in your map, there are some red dots. Okay, do they signify any specific points?
Yes, so I'm not very familiar with geothermal resources in India, but I did some background reading in preparation for this talk. There's a 1991 publication, I think, called Geothermal Atlas of India, and there's a more recent review published this year on the geothermal potential in your country. And I would suggest that it is actually a free resource. You can access that article online, and I can give you the link after the talk if that's of interest. And that describes in detail all of these different springs, including the ones in your state.
Okay, so there is another scientific question that geothermal water contains significant amount monosilicic and polysilicic acids. Is the amount constant in varied subcrustal conditions, and does it impact metal content?
A lot of good questions here from your audience. Okay, most of the scale that forms in those wells is actually silica, and that's because of the significant concentration of monosilicic and polysilicic acids in the fluids. In addition to the silica, which is the biggest problem for scale, there are also other minerals that precipitate. As far as we know, the presence of silica does not significantly change the amount of metals, but the presence of silica does impact on precipitation of scale in the well and indeed in the reservoir. So silica is an issue, but I don't think it really changes how much metal is dissolved in the fluid.
There is another interesting question that can we expect platinum group metals from the brines?
The platinum group metal content of the brines I've looked at is very low. By and large, the metal endowment, and exactly what metal you've got as well as how much, depends on the type of volcano. Some volcanoes would have higher platinum group metal content than others. I think this is where basaltic volcanoes would actually have more metal, more platinum group metals than silicic volcanoes. And that's quite well known in ore deposits. We've actually not really explored, we haven't analyzed for platinum group metals because the techniques we use have a sensitivity of probably 100 parts per billion. And I suspect the platinum group metal contents will be lower than that. It's a good question, though.
So there is another question from Omkarnath Mahante, our president. How would one begin the scrutiny of hot springs in terms of metal content? Do you have simulations of any live hot springs?
Yeah, again, that's a very interesting question. So if we find a hot spring, what we've got is water that's been heated by a magmatic heat source at some depth, or it may be a granite, a radioactive granite at depth. And that the fluid that comes out the spring is hot because of that heat source. The metal content may not be very high, because if no metal is getting from the magmatic heat source into the fluid, it may be very dilute. The big challenge is to analyze the chemistry of springs and reconstruct the chemistry of the deeper fluid. That's possible. It's not very straightforward. So you can get an idea of what's in the reservoir by analyzing the springs, but using it as a direct probe of metal content at depth is difficult.
So there is another question that could you please comment on the geothermal potential of Deccan Trap? Deccan Trap, you know, in Western India, there is a big flood volcanic rocks.
Yeah, so I mean, the Deccan Trap's 60 million years old. The heat has long since died away. So really, that is too old to be within the realms of geothermal heat. And in fact, if you looked at that map of India, there's very little geothermal prospect around the region of the traps. So the volcano doesn't need to be live. It can be long dormant. It can be hundreds of thousands of years old, but millions, in this case 60 million, is too old.
So the next one is Arvind Patel. He asks that how uranium and thorium play the role in the geothermal energy.
Yeah. Okay, so there are two main ways of generating the heat in geothermal systems. The simplest way to understand is that it's simply magma. It's hot molten rock stored at depth. It's at temperatures in excess of 800 or 900 degrees, and that simply provides heat to the overlying rocks. Any fluid that comes off is added to the fluid that's in those rocks. In that case, uranium and thorium play no role. However, another sort of geothermal heat comes when the granite at depth is rich in uranium and thorium and is therefore radioactive. And then you produce radioactive heat, and that also can heat the system. This isn't magmatic heat, this is radioactive heat. So I wonder if your questioner is asking about places, well, one example would be in Cornwall in the UK, where there is geothermal power, but the volcanism is 280 million years old. So it's long since lost its magmatic heat, but the granites down at depth have a lot of uranium and thorium. They're radioactive, and the heat source is radioactive.
There is a similar question. I can simplify it. Somebody asked Roshan. He asked about whether acidic lava or basic lava, is it independent for the metal content or the geothermal energy?
Yeah, so your questioner is quite correct. Acidic lava is more viscous than basic. That doesn't hugely matter in this context. All you need is a source of heat, and I would say that the basic magma is actually hotter than acidic magma. So you have a trade-off between the amount of heat and also the metal content. In answer to an earlier question, I said that generally speaking, acid volcanoes are better for metal-rich brine lenses.
Then there is Vishwanath. He asks about the East African rift zone. Is it a potential zone for this geothermal energy? I think absolutely. Yes.
Absolutely, yes. So one of the countries with the greatest capability in geothermal power is Kenya. The Kenyan geothermal fields are very extensive. They extend up into Ethiopia and down into Tanzania. The geothermal energy potential of East Africa is huge. And also the metals potential is also considerable. I'm very keen to start working, going back to Ethiopia and East Africa and start looking at some of the fluids from East African volcanoes. What's particularly interesting in East Africa is there are aspects of those magmas that make me think we may also have rare earth elements in the fluids. We don't have many rare earth elements in the systems I've looked at. East Africa will be much more promising in that regard.
The next question is, you can answer. The dikes are, whether they are the source of geothermal energy.
Yeah, so your questioner is absolutely right. I showed simulations where we had a conduit up which fluid flow took place. Fluid flow can also take place along dikes. They provide pathways for fluids to the surface. The dikes themselves often aren't great because they solidify and then form a barrier to flow. But if the dikes become fractured or around the margins of the dikes, you can have flow. So dikes are actually a very important part of the fluid and magma pathways to the surface. So yes, is the answer.
So thank you. I don't know how much time we really can continue, Professor Mohanty.
I think another 5 minutes because the questions are turning out to be quite interesting. So if there are very interesting questions, another 5 minutes, and that's about all.
Okay.
I'm happy to answer them, but these are all excellent questions.
Thank you.
Firstly, your audience knows
all the
about
questions and send them to you. And in case you'll be able to throw more light on that. Yes, continue, Dr. Raik.
Yeah, the next is, can geothermal hotspots give any clue about concealed deposits?
Yes. So if I was interested in exploration for geothermal power, if I found a region of geothermal hotspots, hot springs, for example, the next step is to carry out an electrical conductivity survey. And so most geothermal companies in their exploration stage would conduct what's called a magnetotelluric, an electrical conductivity survey. So up in Ladakh, where India is soon to open a geothermal drilling program, they will almost certainly have done magnetotelluric surveys to identify the location and the size of the reservoir. I think for the nation of India, this is a very exciting new development. The fluids are not that hot up in Ladakh, I think maybe 200 degrees, but there's a lot of potential in that area. And yet I can guarantee that no one in Ladakh is looking at the metal content of the fluids as a way of offsetting some of the capital and operational costs of the geothermal plant.
Okay, I think there are not many questions now, or if somebody has the last one, can type it, and then we will close, because we have to have a timeline, and any further questions can also be sent to us in the SGAT, and that can be really answered if there are long questions or very important questions that Professor Blundy would be very happy to revert back to us.
That's it. I think you return it to Dr. Farooq.
Yeah, thank you, Dr. B.R. Naik, for conducting the questions. And
sir,
thank you
can
so
I have
much, Professor.
1-2 minutes interaction with Professor Blundy? I have something interesting to share.
Actually, before you do that, can I just answer the last question? Because that's a very good question. Are any environmental consequences of geothermal metals production? So, along with the metals, there are other elements dissolved in geothermal fluids that we're less excited to have at the surface. Arsenic, mercury are good examples. So the discharge of those metals would need to be controlled. The production of the metals will also involve production of significant amounts of hydrochloric acid, which also needs to be trapped. It could be sold as a resource, but it can't just be released. The production of geothermal energy relies on good fluid flow. And in some parts of the world, that fluid flow is stimulated by pumping pressurized water into the reservoir. That has led to induced seismicity in some parts of the world. I think in those parts of the world, injection of fluid was incautious and was not done very well. But obviously induced seismicity, particularly big seismic events, is a risk. So I think your question there is raising a very good point, that this isn't something you can go into without a lot of due diligence and without understanding the geology of the environment. So yes, sorry, by all means, go ahead.
I think the last question, Dr. Astha, if Dr. Blundy wants to answer, that is fine, or that will be the last question.
Yes, numerous hot springs in the Deccan Traps. Can this be remnant heat for geothermal energy? Interesting. I suspect that the hot springs there are simply because the fluid's coming from very deep. And as your question almost certainly knows, the temperature gradient in that part of India is probably on the order of I don't know, more than 30, 35 degrees per kilometer, and the fluids are coming from some depth. There probably is some fossil heat in the mantle there, but not in the Deccan Trap lavas. Certainly be worth looking at those hot springs. I don't know much about them.
Everyone who have put questions, and although time is short, but I would interact with Professor Blundy for 1-2 minutes. In 2002, I read one article of Peter Hodgig, that was in Canadian mineralogist. He had compared the mining cost in surface mining, what open cast mining or underground mining is going on, and the mining in the underwater sea. This mid-ocean ridges, where you can locate the massive sulfides or the nodules. So there was a comparison, environmental aspects and all that. And there it was compared, and the cost was really put that it is low. Okay. So I was also working on massive sulfide deposits of Southwest Indian ridge, which are black smoker products or white smoker products. I will not go into detail, but I have noted down from my record that in June 2008, I had written an article, a small 2-page article, and I had sent to Nature, and my title was, "Why Not Mine the Brine?" Okay.
Really? Okay.
And the editor of, I had sent it in the News and Views. So Team Lincoln wrote me that, okay, you better contact to the correspondence section and they might consider this. And I had my own drawings and all that, because in the black smoker, this is the metal fluid which is coming and containing 60–70%. When you mine the, with so much cost, and then you cross it, grind it, and all the processing waste, all those things. But and then digest and hydrometallurgical process, you extract the nickel, cobalt, copper, and all those things. But the brine itself is rich in, it is coming out. Then if one can just suck it, just like a straw, so you can have a sip, and from the sip you can suck those brines, and the sip itself is a metallurgical plant. So in that concept I had written, but again it was also from the correspondence section that it was not accepted. I have the manuscript with me with a small diagram and all those aspects. So of course I didn't have those statistical data. It was a thought process in 2008 which I had sent to Nature. Yeah, thank you.
Very nice.
Well, thank you very much for sharing that. So I'll say a couple of things. Firstly, my project that's been running, obviously I didn't know anything about your article. My project has been running since only 2016 is called Mine the Brine. That's the name of the project. MTB, nice. Mine the Brine.
Anyway, I'll say
you highlighted another important point. It's very, very hard to publish new ideas in economic geology. So the article that describes what I talked about today, which is called The Economic Potential of Magmatic Brines, it took me over 4 years to get it published. I had many experiences just like yours. And I think one of the big challenges for us as we move to net zero is we're going to have to think creatively about problems. You describe a very creative solution. Maybe it's not practical. Maybe it's too expensive, too dangerous, too environmentally risky. To propose it doesn't mean to say we're going to do it. It means you should think about it, which I understand was the point of your article.
Yeah. If it would
We
have
need
been,
to start thinking creatively about Earth resources. I was at a big mining conference this last week, and one of the speakers' response to innovation was, innovation is easy in the mining industry. He said, just move more dirt faster. That is not an innovative answer. That's saying, let's just dig a bigger hole faster. We need creative ideas like the one you've just described, but publishing them, not easier. You have my sympathy.
Yeah, I think this net zero concept, it would have been at that point of time for the, this carbon reduction, then probably it would have drawn the attention. And it was too ahead.
Right.
You were too far ahead of your time. Try again.
Wonderful.
Okay, thank you. Now over to Dr. Farooq.
I thank Dr. Naik for conducting this session, and huge thanks to Professor Blundy for making this deliberation so interesting, so captivating. You have ignited the minds of most of the participants, and then you have got so many interesting questions. Thank you so much. Now I request Professor Mahanti, Dr. O.N. Mahanti, our president, to please take over.
Thank you, Dr. Farooq. I'm quite sure that all the participants in this DLS would agree with me when I say that we have been treated to one of world's most authentic voices speaking to us on how volcanoes could be endured. It's actually an oxymoron on the one hand to say that it's a scary kind of picture, but at the same time, it's a beautiful thing as well. And that's what we have learned today over the past 50 minutes. Thank you so much, Professor Blundy, for that. Having said that, and looking at all the questions, I have no doubt in my mind that India should be your focus in the next 10 years, Professor Blundy, and which is why you should look at us. And very important is that the young people who are listening to the lecture of Professor Blundy today, young people, I don't know, only from Odisha or India or maybe outsiders, because I think Professor Ramani is from US. There may be some others also, quite a few of them. And more important is that the young people should get actually inspired. We had invited a number of students. Hopefully it would happen soon. And you showed in your own map, as I mentioned there, a yellow portion. And incidentally, it's about 20 kilometers from Bhubaneswar, the hot spring, which is called Otri, and that found a mention in your map, which is why I commented. And but of course, the water that comes out is not 200 or 300 degrees. It's very small. It's just about 1, and a lot of sulfurated water. People go there for skin diseases, and some people go there for doing their obeisance and mentioning about the god and so on and so forth. But they can also be the source of several kind of metals. Now, one serious point is on the polymetallic sea nodules that Dr. Naik has been working also perhaps at the National Metallurgical Lab in Jamshedpur, as well as at IMT at Bhubaneswar. Polymetallic sea nodules for the past 30-35 years have been of great interest to the Indian mining, metallurgy, and geology community. But then, of course, that's quite rich as far as we are concerned in manganese. And that doesn't work out. The economics doesn't work out unless we have enough cobalt and nickel, which are extractable out of that. Because we have land-based manganese. And incidentally, we do not have much of nickel, which is why Professor Blundy, the largest stainless steel factory of India, is located in Odisha. And what we are doing there is developing stainless steels, but not much of nickel, reduce the 8% nickel to 1% or less than 1%, and replace it by manganese, because manganese and nickel, they have similar kind of places in the phase diagram. And so both of them are actually austenite stabilizers. So there are a lot of areas in which I'm sure that some of our young people and young scientists, researchers, they would have many areas of convergence with you. And people like Dr. Naik, who mentioned that he had generated an idea 12 years back, 14 years back, you should listen to Dr. Naik that yes, don't throw away that in those areas, revive them. So those are about the young people. And incidentally, you mentioned about the IPCC, and we have an organization in Delhi. Have you heard of it? Called TERI, TERI, which started as the Tata Energy Research Institute, but now it is changed over to the Energy Research Institute. And the chairman of TERI was actually the chairman of IPCC, which was awarded the Nobel Prize about 7 or 8 years back. Dr. Pachauri was then the chairman of TERI. So therefore, IPCC and India, they have very close connections. And I'm very glad to share with you the fact that a number of universities and organizations in India, they have taken SDGs as some of their goals. The SDG goals are some of their mission areas. So I'm quite sure many of them would like to be in touch with you.
Sure.
And by the way, I wanted to share with others that yesterday, Professor Blundy spent a few minutes with us, and I was sharing with him the heritage of Orissa and India. And so hopefully we have excited you, Professor Blundy, enough so that you would visit us in person in the near future. Having said that, I have also another request. The Society of Geoscientists and Allied Technologists, now you are more or less familiar with this name. We have a kind of convention that we take the permission of the distinguished lecturer if he would not accept, or he would actually accept our request to become an honorary member of the society. So here is our request on behalf of all our members and also the participants. If you think that it's not a yes or no answer right now, you can take your time, but I want to tell you upfront, it doesn't involve anything great, except that you lend your name to the society so that we will say that apart from the last 8 speakers who have been our honorary members, we would add Professor John Blundy's name as well. And that will all of us, and I will be delighted with that. Professor Blundy, if you agree.
I would be delighted to accept. It would
Wonderful.
Be an honor.
I
Thank you
think
very much.
we'll give a clap at this stage. Thank you. I return back to Dr. Farooq.
Yeah, thank you, Dr. Mahanti. And I will now request Mr. Jain Das to kindly conduct the vote of thanks. Mr. Jain Das, please.
Before that, I request our president formally to virtually give a bouquet, flower bouquet.
Okay. How do we do that? The virtual flowers. They will not carry the fragrance, but you would imagine that the fragrance is there, Professor Blundy. Where are the flowers moving? But I say namaskar. And yesterday I had also said, and today also namaskar. That's how we give a send off to you, Professor Blundy. It has been a wonderful, wonderful experience. I'm sure you have ignited the minds of people who have been listening to you for the past nearly 55 minutes. And the questions actually show that. And thank you very much. Now,
Thank you very much.
Mr. Das, Mr. Das, Jain Das.
Yes, it is my privilege and honor to extend a vote of thanks, but not actually introducing the vote of thanks to a master. We heard an excellent informative talk. As we know, one learns by standing on the shoulders of giants. And today we learn from the master. And probably in India, we will be calling you Guru, the teacher, the ultimate teacher who teaches. And this is a wonderful time for us, and we cannot thank you. For us, always command respect. And we express our respect, reverence, and gratitude. And thank you, and a formal thanks to you to accept our invitation and grace this August platform. And we are all enriched in a lot of knowledge which actually the youngster and others will carry forward. Thank you very much, sir. And
And to
I
the
would,
audience, which has been great.
and then I would thank our president, Dr. Omkarnath Mohanty, who had been the guiding force right from the beginning, and he did all the groundwork. And he could contact Dr. Blundy and convince him and had a lot of interaction. And
I didn't
finally,
have much effort to make actually.
And-
Prof. Blundy was spontaneous in his response.
no, that's
Yeah.
it. And then I thank profusely Dr. B.M. Farooq to anchor the entire show, and also
Dr.
to the
Naik.
end, Dr. Bibhu Naik, and it's really a revelation that he had worked in those areas of back in 2008. It's such a wonderful thing. I think it's a fitting occasion that Dr. Bibhu Naik could do the honor at the end. And I would thank each and one of the participants, the esteemed participants, in spite of a weekend evening, they've all come and shown their interest, and they've asked really genuine, interesting questions. I thank on my behalf and on behalf of the SGAT. With that, I now hand over to President Saab. I think it's time to.
No, I think we'll only say namaskar and thank you very much, Professor Blundy. Now that we have a prime minister, I yesterday told you that we have 33% claim on your prime minister. There is a Kenyan claim and all kinds of claims. So we have some claim. And you also mentioned about our Ladakh. And I thought that the Chinese are also hearing Ladakh is very attractive in terms of geothermal energy. That's another reason why it should also be occupied. But anyway, those are on a lighter vein, but wonderful, wonderful. And so that'll be a formal letter to you, Professor Blundy. Thanks very much. Namaskar.
Thank you very much.